Okay. Can everyone see my slides at this point?
Yes,
Yes.
I can
Excellent.
see.
Okay, I'm going to go ahead and get started.
Go ahead.
Okay, thanks everybody. I'm here to present my research on political yard signs in presidential elections. My name is Catherine Schmitzians and I go by Kat. Background for this project is my research question, which guided it, which is, can an easily observable indicator like political yard signs predict presidential election results at the precinct level? So the political yard signs I'm talking about are the ones pictured here, like the ones pictured here. And a precinct in the US is a geographically contiguous area within city limits, and the residents within that area vote at a particular location, which is also called a precinct. In Michigan, the precincts are roughly equal in population size. They're about 2,000 each. My data set consists of 17 randomly selected precincts in Dearborn and Dearborn Heights. There were two phases of primary data collection here, so I'm presenting data that I collected myself. The first one took place just prior to the presidential election last year. I canvassed the precincts either in a car or on my bike and counted the number of houses with a presidential sign and recorded the candidate of choice. So I only counted one sign per house, even if a house had multiple signs. The reason is I was looking for an indicator that would indicate that a person had made a choice of candidate to vote, because that's what I wanted. I want to predict actual voting behavior here. So I figure one sign at a resident means a choice, two signs, three signs, four signs, that's just enthusiasm, and I wasn't interested in that. The second phase of data collection actually happened very recently when I found out that not a lot of data is aggregated at the precinct level in the US. It's mostly electoral data. You can get it from your county clerks and it's all readily available. But the problem with electoral data is it's very highly correlated and there's a lot of multicollinearity problems if you use it in modeling like this, because I could build you an excellent model predicting Biden vote from Gretchen Whitmer vote in 2018. But with only 17 observations, no other predictor would have a chance in such a model. So what I wanted was race or economic information about these precincts. And I'll tell you about what I did to fix that problem. These are just some artifacts from the first data collection because it took a long time and it was pretty involved. So I just wanted to show my Strava map of the last bike ride I took. I canvassed 3.5 precincts on that day because the election was the next day. And then on the right side, you see the precinct cards where I would write down where I'd been and where the signs were. Resulting measures precinct level count of Trump signs and Biden signs. Houses with those signs. Phase 2, I used Google Earth. Okay, so Google Earth, I thought I want race and economics for these precincts. I can't observe race from space, so I focused on the economics. Using Google Earth, I employed the following procedure. I took all the precincts that I had sampled and I divided the residential areas in the precincts into squares of equal size. Then I sampled 2 of those squares per precinct and averaged the counts, and counted the houses and averaged them. This actually gives a housing density measure because the denominator of this would actually be that same area that I was measuring in each case. I also counted the total number of swimming pools in each precinct. The reason was I thought this might be an economic indicator. Why pools? I'm just going to do a little digression about Greece. In Greece, tax collectors about 10 years ago used Google Earth to count the number of swimming pools in the suburbs around Athens. From tax records, they expected 324. They actually found 16,974 swimming pools, and it ended up collecting billions in back taxes based on stuff like that. So that's where I got this idea from reading that article. This is some descriptive statistics about Dearborn and Dearborn Heights and how they compare. So Dearborn's about twice as big as Dearborn Heights. They're comparable economically, although Dearborn has higher household income and higher property values. What you see on the right-hand side is actually another artifact of this study. This is something I created where the white map is Dearborn precincts, the multicolored map is Dearborn Heights precincts, and if you look closely, you can see all my little squares, how I see it. So how did I decide on what to model in this situation? Well, I decided to predict Biden vote. I also have the ability to predict Trump vote, but that's like actually the next stage of this analysis, I think. My first goal was to create a model that could be used in the next presidential election. Here's the reason. I'm about to tell you all about cross-validated test MSE that I got for my models, but the real test MSE is going to happen in 2024, right? So what I wanted was a model that contained only variables that I could measure prior to the election, so I could test it out if I chose to do so in 2024. Second goal was to build a model that could be estimated reasonably well on a sample this small. Professor Schinke gave me the excellent advice to keep it simple. In this case, there's not a lot of power when you only have 17 observations. So I made a decision to include one electoral variable, which is turnout in prior elections, as my initial variable in my models. And then I added the variables that I measured to the model to see if they would help. These are the descriptive statistics of the information I included in my model. So here's where I get to talk about my data transformations. So the Biden proportion, it's a ratio variable. So it is not normally distributed, and there were lots of nonlinear things going on with the independent variables and my dependent variable before it was transformed. I ended up using the transformation that is given in the note here, the arcsine transformation, which is commonly used to fix this type of problem. And it did a better job than a log transformation, which I also tried. Turnout in 2018, as you can see, was much lower than turnout in 2016. That's normal because presidential election years bring out the people. The housing, so I had this housing count, this density, and I transformed it into a z-score. So essentially what this is I have, what this variable, the housing density score is in units of standard deviation. So you can see that my 17 precincts go from negative 1.26 standard deviations below the mean for the 17 precincts and up to 2.12 standard deviations above the mean. And then the pools were an issue. Here's why. Dearborn and Dearborn Heights are very different in terms of pools, with only 11 observations in Dearborn and 6 observations in Dearborn Heights. I was able, using a Welch's 2-sample t-test, to confirm a significant difference between the mean number of pools that I counted. Dearborn Heights, they're extremely thick on the ground compared to Dearborn. So actually the way to deal with this, in my opinion, is to use an interaction, right, between city ID and the number of pools, because there's obviously a different intercept going on in that type of model. The problem is the 17 observations. The only way I could get an interaction to be significant was to only include the pools variable and the interaction, and that's not what I really wanted. So instead, what I did was I created a sort of a variable. I divided the number of pools by those average houses that I counted in those 2 squares, and they gave me sort of this continuum of pool density. It's not perfect, but it's what I could do. This is the scatter plots of the variables that I considered. The orange outline shows the ones that you should be focused on. So those are the ones where the arcsine transformation of the Biden percentage, or proportion actually, is on the y-axis and the independent variables are on the x-axis. You can see some different trends in the data. I don't really like the, I think I see a curve here, actually, in the turnout 16 data. I tried to do polynomial regression to deal with that, of course, or, 17 observations. Okay. So this is what I did. I used multiple regression. I have a tiny data set. So I used leave one out cross-validation to estimate the test MSE. In all the models, the dependent variable is that arcsine transformation, 2 times actually the arcsine transformation of the Biden vote. I've put stars on all the variables that were significant when I initially estimated these models. I just gave you that they're significant at the 0.05 significance level. Turnout in 2016 was significant from the outset. Adding Biden signs to turnout in 2016 actually gave me a really good improvement in my test MSE. I was very happy to see it. AIC also decreased. Then I added housing density score and got another decrease in my test MSE. Wonderful. Okay, so I was very happy with that. Then I added pools, not significant. Also, the test MSE went up. So that's the end of that. Turning to the turnout in 2018 model, turnout in 2018 was not significant when it was included as the only predictor. When I put in Biden signs, it became significant. Test MSE went down, yay, right? Then I added housing density score, also significant. Test MSE went down again. Then an interesting thing happened where I added pools. It was not significant, but my test MSE went down. Here's the models I'm choosing, these two, okay? I realized that everything lines up for the turnout 16 model and things aren't quite lining up for the turnout 18 model because I do have a model up there that has a lower test MSE. Thing is that pools variable is not significant and the test MSE is so close, it really makes me wonder if there's a statistical difference between those two. And so I would not pick that model, even though some of the things say I should, and perhaps Professor Schinke is going to tell me that I should. Here are the winners. The winners, model 16 is what I call the 2016 turnout model. I give the population model that I'm actually estimating up here, so you can see it. And then model 18 was based on the 2018 turnout. Again, the models given, the only difference between these is that it's 2016 versus 18. The parameter estimates that I got from my sample are given below with standard errors. All of these have stars on them in terms of being significant. You can kind of do the t-test math in your head and see that these are really quite large t values for these, and the f-test was significant for both. So turnout is negatively related in both models to Biden vote in 2020. So lower turnout in these prior election cycles signified higher Biden vote in this election cycle. I'm not going to give you the for every one increase in this increases by that, because it's transformed, right? My dependent variable is transformed, and the arc sign transformation actually like attenuates the tails of the distribution. So it's not a simple one-to-one that you can interpret from this, but you can look at the direction, and the magnitude as indicators. Biden signs were positive predictors of Biden votes. Awesome, right? That's really what I wanted to see. So I was very happy to see that. That happened in both models. And housing density score was negatively associated with Biden vote in both models. So as housing density increases, Biden vote goes down. I'm just not sure about that, because there was definitely a big difference in voting behavior between Dearborn and Dearborn Heights overall. So looking at the right-hand side, I have my test MSE and the AIC, but looking at the test MSE, the model that I would ultimately choose would be model 16. It has I see it, yep, it has the lower test MSE. And it makes sense that the model that contains the turnout in the prior presidential election might have more to say about what voters will do in the next presidential election, as opposed to the off presidential election years. And this is my reference to a very cool article, if you want to read it. And that is the end of my presentation. Thank you so much for your attention.
Yeah, thank you, Catherine. It's very organized presentation, and yeah,
Thank
it
you.
looks very interesting result.
Thank you.
Do you have any questions? I mean, the audience.
Hi, I have one. Hey, Kat.
Hi,
I
Jacob.
loved your analysis and like how you gathered all of that data. I just had one quick question about the precincts. Did you look into if the precincts were affected by gerrymandering?
So that's a really good question. The districts are affected by gerrymandering, but the precincts are not. So precincts are just a geographical division within, and the cities seem to do them in a pretty standard way in terms of trying to fit in population size. The area is hugely different, but that mostly was taken care of by like the business area as opposed to the residential areas. The residential areas were similar. So yeah, if I was doing a district level analysis, gerrymandering absolutely would have been a big thing. But in the precincts, it's less political because nothing really depends on it. How those are drawn, nothing really depends on that. So.
All right, perfect. Thank you.
Yeah. In case anyone's wondering, gerrymandering is the process of drawing districts so that you make an outcome happen. So you put the voters in the districts in such a way as to make it a safe Republican district or a safe Democratic district. And in Michigan recently, we passed a law to have an independent commission of voters to draw our districts to try to stop that from happening. So fingers crossed.
Any other questions? Yeah, I will make some additional comments by email. So yeah.
Wonderful. Thank you.
Okay, thank you so much.
Mhm.
Okay, so next presentation, Ian. So the Ian, can you share the screen?
Cool. Can you see my screen okay?
Yes, yes.
Okay, awesome. Actually, I'm going to switch my headset because I noticed I'm getting some feedback through this one. So if you could give me 1 minute, I'll switch that over. One sec.
I just want to share with the class, that's the only time I ever came in under time. Like every time I practiced, I was way over.
um, hello.
All right. Can everyone hear me okay?
Yep. Yeah, you can start now. Do you have any trouble? You can start now, Ian.
Hey, can everyone hear me okay?
Yep.
Okay, I apologize. I'm worried my headset might die, so I'm going to try to get through this as quickly as I can. Apologies.
I cannot hear you. Okay, so maybe the next presentation, maybe the Ian, you can do it later. So maybe next one, any other person?
I can start.
Okay, so Vahid, can you share the screen?
Yes. Can you see my screen?
Yes.
So just a moment.
Yep.
Hi, everyone. My name is Vahid, and my project is about determining socioeconomic factors that affecting individual investment decision. This is in these slides, we have my presentation outline. First, we have short introduction and then data description, methodology, and finally we can go to results and summary. As you may know, investment behavior decision has become a popular subject during these recent years. Many factors affect people's investment decision, but in my research project, I mainly focused on socioeconomic variables like age, income, household size, or employment status, and some other socioeconomic variables. My project objectives are two main objectives. First, to analyze the impact of these variables on people investment decision. And the second one is to do a comparison between some classification methods. I have a comparison between logistic regression, LDH, UDA, and K nearest neighborhood. So as you may know, I have collected my data with online questionnaire. I had 221 observation. After some data cleaning, I had 204 observation for my research project. And in this table 1, we can see my variables description. I had 6 main independent variable and 1 dependent variable. Investment decision. I have asked respondent to have they ever had any investment in stock market or cryptocurrencies. So I used an binary classification models for this, and I used these categorical variable for describing my dependent variable. As you may know, all of my variables are categorical variables, because somehow with online questionnaire, it's a little hard to collect some continuous variables. So I prefer to use categorical variable for independent variable. In this slide, in the figure 1, we have living places of my respondents. As you can see, most of my respondents are in Michigan, and then California and Texas and other states. In figure 2, we can see age distribution. I divided age distribution into 3 different categories. First, between 18 and 30, then 31 to 50, and then above 50. In this bar plot, figure 2, we can see that most of my respondents are young people, and mainly about 20 or 25 people are above 50. In figure 3, we can see annual income distribution of respondents. We have mainly even distribution. All groups have same about 25% of all respondents, and it will help us to describe investment decision by income in a good way. In the right hand side, we have employment status. Most of my respondents are employed, either full-time or part-time, and about 20 people not employed. So we have variables correlation plot in these slides. We don't have multicollinearity as a problem, because correlation coefficients are not high between variables. The highest one is for between income and investment. That is my response variable, that is 0.4. So we don't have multicollinearity problem for our logistic regression. So I used binary classification methods, logistic regression, LDH, UDA, and KNN, and I had some performance analysis with accuracy, error rate, precision, sensitivity, specificity, and mainly area under curve, AOC, that is the area under ROC curve. So we have short description about performance analysis of these classification methods. As you may know, we define accuracy, precision, sensitivity, specificity, and area under curve as these slides. And then we can go to results. As you can see, my logistic regression model, income has the most significant effect on people investment decision, and then we have employment status, and then being male and being single, but some variables are not highly significant, like household size and also age is not high significant. Age group 2, that means between 31 to 50, are somehow significant with negative sign that shows maybe when people get older, they don't want to have many investment, they don't want to take risks maybe. So for this regression model, logistic regression, I have 0.23 training error. Also, I used Python Biogems, that is packaged in Python for classification and choice modeling. Mainly, I use this in Python to calculate row square and adjusted row square for my model, because R doesn't easily give us dot index. So as you can see for my model, we have row square equal to 0.3 and adjusted row square 0.21 that are pretty good indexes for classification problem. So as you can see, the results are pretty similar with the previous slides, because again, income and employment are also significant here. If we can see, even for example, income in level 4 has a same coefficient as the previous one in the R results. So I'm not sure what procedure are used, but Python using maximum likelihood method, and they give us similar coefficient for variables. And here in these slides, I have a table of comparison between different binary classification methods. As you can see, KNN methods has best performance between all other methods. KNN methods with K equal to 15 has best accuracy, error rate, and AOC index. So I tried many different K numbers. So I tried K equal to 1, K equals to 10, but as you may know, there is no specific procedure for finding optimal K in KNN method, but I read somewhere that you can use a square root of total number of your sample size. So my sample size was 204. So square root of that will be 14.3. So I used 14, 15, and 16. And then I realized that K equal to 15 give me the best performance for these classification methods.
So is this the cross-validated or what method?
Yes, I used training error and tested error. I separated my my sample size 204 into 2 different parts, each one 102, and used test error for achieving these indexes. So this is it. It was my presentation. Oh no, I have one more slide. And in the summary, as I mentioned, income level has the most effect on the individual investment decision. Also, job status and being male and being single are all significant, but some variables like household size, like age, are not highly significant. And in the comparison between the classification methods, we saw that KNN methods has best performance among all other binary classification methods. Thank you everyone for attention.
Okay, thank you so much, Wahid. Any question from the audience? So I think it's pretty organized. So do you have any question? Maybe so that you collected data, right? So
Yes.
so what kind of so how did you advertise your survey? So
Well, mainly I distributed my online survey in some student groups. I asked some of my friends in other states, other places to distribute this between their friends and their family to collecting data. As you can see, maybe in my data description, that most of the respondents are from Michigan because we are living here, and then some other states. These are the place where are my friends.
any other questions? Okay, so maybe we go to the next one. Who will
I can go.
Ian? Now, sorry.
Or if Ian can
Ian,
go as well.
Ian, are you prepared or
I am.
not yet?
I think I'm prepared. If you can hear me, I should be good to go.
Okay, so you
I
can go now.
apologize about the
Then
audio
after
issue.
that, Raymond. Okay, so Ian. Okay, so can you share the screen?
Sure. Wonderful. Okay, can you see my screen okay?
Yes.
Awesome. Okay, I will dive in. So hello, my name is Ian Kwiatek. I performed a regression model comparison with a time series data set. So my introduction, my motivation was to understand how to analyze a time series data set. I wanted to use various forms of regression, and then I wanted to compare these forms of regression for quantitative and qualitative accuracy. My two goals for the presentation were to accurately predict the rented byte count by hour with a high level of significance, so variance being greater than or equal to 0.9, and also to determine if there was like a clear winner for the best learning algorithm for regression analysis. And so my presentation is broken down into 5 sections. I have the data preprocessing, the lagged variable creation utilizing Lasso, the train and test data creation, the comparison of models, the models that I use for linear regression, Lasso, decision trees, and random forest, and then I'll conclude the presentation. So data and preprocessing. Abstract about the data set contains the count of public bikes rented at each hour in Seoul, which is South Korea's bike sharing system, with the corresponding weather data and holiday information. I sourced this data from UCI's machine learning repository at the following URL, and the sample size consists of 8,760 hourly entries for a total of 365 days, so that's a full calendar year. A little bit more about the variables. So there were 14 variables presented in the data set. I had to create 24 categorical variables for each hour. I also had to create, at this point, an unknown number of lagged hour variables. And variables range from things like date to weather specifics like humidity and wind speed, as well as what season it was, if it was a holiday, and if it was a functioning day. The data set was super clean. There were no NAs present, which was awesome. I did have to clean up the column names a little bit to remove spaces and special characters. And I had to treat or convert holiday, season, and functioning day into factors, which allows for automatic creation of dummy variables in R. Part 2, the lag variable creation. So this is the first time I've dealt with a time series data set, and I was really excited because I feel like a lot of data that we see nowadays, whether it's COVID numbers or stock statistics, are all time series. And so the first question I had was, I know I need to create lag values, but how many do I want to create? And 3 options I came up with were, first, I could just use intuition and kind of guess which lag values might be the most statistically significant. I could also use as many as there are still helpful to the modeling process. So increasing my lag values all the way up until I start to see degradation in my models and then decreasing them back down. But I really wanted like a finite way to create my lag values. So I ended up using Lasso to find which lag values were statistically significant. So in practice, we can use the past 12 hours, the past 24 hours. In our example, I actually used 48 hours as possible lags. We then use Lasso to figure out what we actually want to have in our pre-filtered lag values moving forward, which we'll then incorporate with our other 14 values that were originally presented. So here's the intuition model. Using an autocorrelation function, this gives us an idea of which lag values are statistically significant. And really, there's no surprise here, right? The lag value that's most significant is right now, less 1 hour. When we look at right now, less 23 and 24 hours, we see that that's also highly statistically significant. And those 2 points are modeled with the red arrow above them. Less 23 and less 24 lag values are just the same time as right now, yesterday. So that makes sense. But the real question is, how many lags do we want to incorporate? Can we do it in automated fashion so we're not really guessing and checking? And I found that we can use Lasso as kind of a dirty way to determine this for us. So we're going to run Lasso. We're going to look at the coefficients of Lasso. Any non-zero coefficients mean that Lasso likes the variable and will probably want to keep it. And if we have any zero coefficients, that means that Lasso said it's not useful, let's throw it away. So when we ran our initial Lasso test, we found that nearly all 48 hours or 2 days were statistically significant. Not super helpful, right? We end up with the same data set we started with. So the logical approach was, let's increase the penalization rate to determine which features are more parsimonious or more relevant. So we defaulted with 1, we increased it to 10, and we still had a ton of lag values. So I increased the penalization rate to 100. And what that allowed me to identify were 5 statistically significant lag values that were in line with what our intuition told us would be statistically significant. So those 5 lag values were 1, 23, 24, 47, and 48. And you can see in the table on the right-hand side, there's statistical significance. We can also see that basically all the other lag values kind of fall away. Cool. Now we have our data set. We have our lag values, which we can then build our models with. So let's build the train and test data. So in order to create our train and test data, we had to do some upfront conversions. Because seasons had 4 levels, which is spring, summer, fall, and winter, the problem is that we have a linear dependency. And for linear regression, when there are linear dependencies, things will just straight up fail. So we also had to convert data, we had to convert the date from European to US styles. We ran into some issues there as well. And on the right-hand side, you can see what that conversion looks like. After removing the linear dependency, kind of what the data looks like. So splitting the data into train and test sections. So we simply picked a date, which was the 10th of October for 2018. We said our training data is going to be 305 days, and our test data will be the remaining 60 days. So it's kind of a 84-16 split. And you can see here that 1,440 hours created our test data, 7,320 hours created our training data. So now I'm going to dive into the regression model comparison, and we're going to look at it from both a quantitative and a qualitative approach. So the models that were utilized. We started with linear regression because it's a good baseline. We've used it throughout the past couple semesters, and it kind of just made sense. We also used Lasso because it does feature selection, and we included decision trees to add some nonlinearity, and random forests to also add additional nonlinearity, but to also add some diversity into the models. So when visualizing the model, there's 2 values that we focused on. First, we focused on mean squared error. So we compared mean squared error across different learning algorithms to compare and choose the MSE or test error that was the lowest across all 4 algorithms. It's less useful as a measure alone, But in this specific example, we found that it was a really good way to compare our different learning algorithms. And we also used variance. So in addition to MSE, we used R-squared to compare learning algorithms. So when using training data, we learned upon R-squared is bounded between 0 and 1. When we use test data, R-squared is bounded by 1, but not bounded below 0. So what does that mean? If we get an out of sample R-squared or test R-squared that is beneath 0 or negative, this implies that our prediction model is poor and that we probably would have been better off predicting the mean rented byte count instead. So let's get into the results. Here is an initial results of the linear regression. So we can see here that the bluish line is our true rented byte count, and the pink or red line is our predicted rented byte count. And we could see that linear regression did a pretty good job of matching the true rented byte count. We can see, however, that at the peaks, linear regression starts to fail a little bit, and it's not wildly accurate, but it does a good job of modeling the true rented byte count. So here are the results. Decision tree performed the worst. It had the greatest mean squared error, and it had the smallest variance. Linear regression and Lasso, interestingly, performed very comparatively with one another, but Random Forest performed the best by far compared with the other learning algorithms. It had a significantly smaller mean squared error and a significantly larger variance.
So this is the test error.
Correct.
Okay, yep.
Yep. And from a qualitative perspective, we also wanted to look and see how did our model track, or how did our various models and forms of regression track against the actual data. And so actual is presented in pink or red, and you can see the various colors. One thing to note is that linear regression, because it's not bounded by 0, we can see that it actually dips into a negative territory. And this might contribute to a degree of why linear regression performed worse than some of the other models. So to conclude the presentation, we reflect back on our goals. Can we accurately predict the rented byte count by hour with a high level of significance? Yes, we were able to do that using Random Forest, which provided a significance level of 0.91611. We also wanted to determine if we can define a clear winner for the best learning algorithm for regression analysis. And again, Random Forest was the clear winner with a low mean squared error of 28,930 and a high explained variance of 0.91611. I was really surprised by the variance. That was the best variance that I've seen throughout my presentations for the last couple of semesters. So what did we learn? Time series analysis requires significant upfront work to create the model. A lot of the work that's done is just to build the model. Applying regression is actually relatively straightforward once you have your model created. The autocorrelation function offers an easy way to visualize significance of lag values. However, Lasso is probably a better way to identify which lag values are most significant, and it allows the user to define penalization rates so that you can trim down the data that you're getting back or the results. From an analysis perspective, we found that mean squared error and variance are ideal candidates for analyzing and comparing the accuracy of a learning algorithm. We found that Random Forest algorithms performed the best by far, producing the smallest mean squared error and the largest variance. We found that linear regression and Lasso algorithms performed comparatively well. And surprisingly, we found that decision tree algorithms performed the worst, producing the largest mean squared error and the smallest variance. I'd like to thank you for joining me and listening to my presentation. I invite you to send any questions, comments, or suggestions to my email, and I would be happy to share with you any of the information that was presented today. Thank you very much.
Thank you so much. Yep. do you have any questions?
Yes, I have one question. It was a really good presentation. Just one point about slide number 14. You said that there were some dependencies between these data. Yes. How did you convert data from European to US style? I didn't understand that part.
Okay, good question. So European style, I believe, was year, month, day. And the way I expected to see it was day, month, year. So I simply reorganized basically the columns of the date so that I could display them in a fashion that I guess we are probably more used to seeing here in the United States.
Okay, thank you.
Welcome.
I have a question about the same slide. So how the season, 4 seasons has been determined in this data set?
So 4 seasons were, what do you mean by how were they determined?
I mean, for example, what is the definition of spring?
That is a good question. Basically, as I understand it, the way it works is it zeroes out all of the other seasons and provides a 1 value for each given season. For example, let's see, 1, 2, the third kind of section down on line 49 through 54, I believe that illustrates basically how any given season is zeroed out. And then for the season that's present, like winter.
I mean that, for example, the spring is just determined by for example, the March to May or something, or it's determined by some.
Okay, understood. I apologize. So that's predetermined. It's predetermined in the data set. I don't know what the date boundaries are for it, but I'm going to assume that it probably matches like what, from a calendar perspective, what we say is spring, summer, winter, and fall.
Okay, so just like 91 days each or something.
Pretty much, yep.
I see. I think it's also another statistical question, how to optimize the definition of the seasons to predict the spike.
Definitely, and that was part of
the
seasons presented part of the concern for the training and test data, simply because we knew that the data for winter was going to be significantly different than the data for fall. And so that's definitely something that I adjusted and played around with to make sure that there wasn't a dramatic impact to the model that was created.
Yep. So do you have any other questions from the audience?
I have a quick one. I think you sort of answered it, but would you be able to reiterate, how did you fix the seasonality? So for example, there might be more sales for or rented bikes in spring and summer as opposed to winter. So how did you work with that disbalance?
So I ran the model for various I created models for various seasons. So I just adjusted basically where I had my training and test data, and I didn't see any major statistical significance when I adjusted those dates for creating the training and the test data. So to answer your question, while I considered it from an analysis perspective when I was doing testing, I didn't consider it in terms of adjusting how I went about creating my model, because I didn't find any significant statistical changes based on the ranges that I had created for various models, if that makes sense. So I changed basically that October 1st date to multiple different dates to build different models, and I didn't see much of a difference between the models as a result of doing that.
Okay, sounds good. Thank you.
I think part of that too might be that although it's winter in Seoul, I don't think the temperature and the changes in seasonality are the same as we see here, like in the Northwest. So it's not as dramatic of an impact for winter in Seoul as it is for winter in Chicago or Detroit.
That makes sense. Thank you.
You're welcome.
I think if I remember correctly, Korea does have pretty cold winters.
Right, I heard of it, yeah. Maybe it's a little better than Chicago, maybe. Yep, okay, so thank you. And maybe I just want to make sure that everyone is here to present the rest of the presentations. So the Ian and the Vahid and the Catherine has already finished, and the Raymond and Colin is here, and Laura, I think the Laura is here also. Okay, I see. So maybe that we will take maybe 3 minutes break, and we start maybe 7:57. And Raymond may be the first one to present. Okay. Okay.
If everyone's still there, I just wanted to mention that I did go back through and look at the temperatures for December, January, and February in Seoul. And while they're not quite as cold as Detroit and Chicago, there is a significant temperature difference with the mean high and low being somewhere around 40 degrees.
I see. Yeah, it's during the break, but just I have to make one comment on the Vahid presentation. So that you used the some rho square statistic for the logistic regression. So obviously, for logistic regression, we don't have the correlation coefficient, right? But we have still we can calculate the likelihood, deviance, basically likelihood-based information, and we just transform that into the 0-1 scale, and that is the rho square for the logistic regression. So I think, yeah, that's true. The R does not report that number in default package. Yeah, just to advertise, I think the 6840 may cover that statistic, maybe.
Sorry, Professor, could you repeat 6840?
Yeah, 6840 is applied regression analysis, the STAT60. Okay, so maybe I use the chat 6840 applied regression analysis. This is still applied statistics class. We have the more theory on the generalized linear model that includes the logistic regression, count regression, and so on. And it discusses those materials, the rho square for logistic regression. So yeah, you can. This will be offered every fall semester. So if you have more than 5% chance to take the course, just register early so that the course will not be canceled.
Thank you, Professor.
Sure. And also maybe I have to advertise another one. So 7820, so this is the advanced statistical theory. This is more a theoretical course, and yeah. So we will have another new statistician next semester. So I'm not sure who will teach which course, but advanced statistical theory, yeah. So last year I used the machine learning textbook to discuss the neural network and some other stuff. But yeah, it depends on the instructor, really. Okay, so now we want to start the next one. So the Raymond is here. Okay, you can share the screen. Yep. You can start.
Can you see okay?
Yep.
Okay. So my study was focused on predicting SARS-CoV-2's US state government responses. So basically, I'm trying to wanted to see if we can predict whether a state will relax or tighten COVID restrictions based on certain variables. So let's go through the introduction. So like I said, I'm trying to predict if a state reduces or increases COVID-19 restrictions based on certain variables. It's not a study of how effective a state is at controlling a virus or what methods are the best. So I'm not looking at whether or not vaccines are effective, whether or not wearing masks are effective, whether or not forcing everyone to social distance or telling everyone to stay at home. That's not what I'm looking at. I'm just looking at whether or not a state will relax or tighten restrictions. So that's to make everything clear. So let's talk about the data. I'll first focus on the independent variables. The first ones I got from the CDC. It's the total death in cases, new deaths in cases, and presumed deaths in cases. The CDC, they have every single state, CDC and health centers, they have to update daily the number of new deaths and cases they have, and as well as total deaths and cases. So I was able to grab it from the CDC website. Unfortunately, it's all daily updates, so it became a hassle to try to summarize it into a week. I decided and talked with Professor Shinki because of the problem with time series. If you say took a data from January all the way to April, there's it's a time series data set. I don't know how to deal with time series. Maybe Ian could help me in the future. But so I decided after talking with Dr. Shinki that we should just I should focus on 1 week, the amount of cases and data based on that 1 week, and then determine whether the state will relax or tighten restrictions. The next one came from Worldometer. This was basically figuring out how many tests were done. The tests per million or 1 million. So in 1 million people of that state, how many tests were done? Same thing with deaths and cases per million. This was done with the Wayback Machine. As Worldometer, they constantly update their COVID data. So the next one is P and M. This is Pfizer and Moderna's vaccines. It's basically done by a weekly basis. So every week the CDC, they have a data set where they dictate, or maybe it's the companies that dictate it or the government, I'm not entirely sure, but they allocate how many vaccines go to which state. And it's also, the data set originally, as you know, both Moderna and Pfizer, they take there's a two vaccines, or there's a 2-shot vaccine for both of them. So when they allocate it, both vaccines are basically identical. So the first vaccine and the first shot and the second shot, they're both identical. The numbers are identical. So I just decided for simplicity's sake and to avoid the collinearity, I just added them up. So Pfizer's, the number of vaccines allocated is the sum of both the first shot and the second shot, and same with Moderna's. Next up, we have the dependent variable. That's the restriction level. This was actually pretty tricky to decide what to do. But in the end, I decided to do based on the status of restriction. So it's a classification variable of 5 levels. Level 1 is restrictions are completely lifted, so there's no restrictions whatsoever. Level 2 is restrictions are eased off. So basically let's say you go from a stay-at-home order to, say, restaurants are open at 50%. That's basically, you just lighten off the restrictions. The level 3 is no change. So no change could also mean you've lifted your restrictions for 1 month and you still haven't changed it. I decided to put no change there, as it could also be you have maxed out stay-at-home orders, no one's allowed to leave the home for a month, and you keep it there. So I decided, because of those two extremes, it made sense to put no changes at all at level 3. Level 4 is the reopening is paused, and then level 5 is restrictions are strengthened. And this data, it came from USA Today. They have basically an article that updates pretty much daily or weekly the restrictions. So this is based off February 20th, 2021, as that's the week I focused on, February 14th through the 20th. So as you can see, you have the blue, that's level 2, that's restrictions are easing. I guess that's burgundy. That's level 5, that's the restrictions are tightening, that's like Arizona and Arkansas. The yellow ones are reopenings are paused, so that's level 4. The gray ones are restrictions are unchanged, so that's level 3. And the green ones are restrictions are lifted, so that's level 1. I also just focused on the 50 states, so I ignored data from like Puerto Rico, US Virgin Islands, and etc. The CDC data did have that, but because I couldn't find data for the restriction levels, I decided to just focus on the 50 states. So one thing I was originally wondering is to create a severity index. So that's basically how severe a state's restrictions are. But the problem with that was, first of all, there's a lot of legal papers to read. You have to go through tons of executive orders from state governors. You have to look at legislative actions. You have to read court decisions. That became way too much of a hassle for a single person to do. Plus, I'm not a lawyer. So in the end, I decided to opt out of doing that. Also, it's very difficult to quantify the severity of the restrictions. As an example, we can look at Arkansas and Arizona. So for Arkansas, Arkansas has a mask mandate, and it also requires restaurants, bars, and clubs that serve alcohol to close by 11. And he also issued guidance to Arkansas churches. And in Arizona, you see that the governor expanded health and safety requirements for public events, but he also relaxed regulations on restaurants. But he also declared that businesses that disregard safety guidelines would face closure. And he also decided not to implement a statewide curfew. So as these two examples, you can kind of tell that Arkansas is probably a more severe or tighter restrictions than Arizona, but the question is how much. So that was a bit of a challenge. There's actually a really nice study done by the University of Oxford where they actually have a index of severity by government response for the whole nation, where they took the severest state or provincial level decision and they applied it for the whole country. They did that, I think, for almost every single country in the world. It's very interesting, but it's pretty complicated how they did the index. And like I said, I don't have that much time to look through all the legal papers for 50 states. So I decided to just focus on restrictions easing and tightening rather than the severity. So before we go on, I'll notice some interesting things I found about the data. Both the Pfizer and Moderna vaccine allocation data, they had very strong correlation with total cases and deaths as well as new cases and deaths. So that might have led to collinearity problems. But at least the good news is it appears the government is allocating the vaccines based off of cases and deaths rather than, say, population. Another thing was the restrictions or the dependent variable had almost no correlation with any other variable. There's 13 in total. Also, total deaths and cases have a very slight negative correlation with restriction. So if you were to just look at it, you could say that tighter restrictions do lead to lower deaths and cases. So the methodology, I chose basically 3, as I couldn't get QDA to work for some reason, probably some data frame issue. But so I decided to focus on logistic regression, LDA, linear discriminant analysis, and KNN. For logistic regression, I use multinomial mainly because I have 5 response classes. So as I was reading, they recommended multinomial for if you have more than 2 response classes for logistic regressions. So for the evaluation, I focused on mainly on the success rate and the error rate. Basically, I felt that if we just focus on whether or not they could accurately predict the state's tightening or loosening, I felt that was the most important thing that everyday people will want to know, and people like us as well. So let's look at the results. Logistic actually had the best result at an 80% success rate with a 20% failure. LDA had a 50%. KNN for 1 and 3, they did really poorly, while KNN at 10 and 50, they did the same, and they did the same as LDA. So what can we draw from conclusions? So multinomial logistic regression had the best result. However, its p-value was at 0.05469, so it's slightly above the a typical p-value that we expect is 0.05, so it's not really significant, sadly. LDA and KNN with K at 10 and 50 had the same accuracy, but they had very different prediction errors. For KNN at 10 and 50, in the test set, they believe that all of the test set should have been easing, whereas for LDA, it believed that 3 of them should not have been easing, and it was actually correct in 1 of those instances. But that was the main difference between those two. As for KNN 3 and 1, they just did really poorly. So improvements, I felt like probably there were some more variables that could have impacted a governor's decision. One of them is probably economic ones. As I was doing it, I later realized probably economics probably plays a huge role in a governor's or a state legislature's decision. As if your economy is struggling and the people are really poor and they need money, you probably would rather keep the state open rather than closing it down. So that's probably something that I could probably look into. Another thing is government and legal. So most of these restrictions and easings, they're done by the governor through executive orders, but because of 50 states, each state has its own constitution. Each governor has different abilities and powers. For example, if in Michigan, Governor Whitmer, in the early stages of the coronavirus, she did her emergency action, I believe, but the Michigan legislature later sued her for overreach as she did it for way too long, and the Michigan Supreme Court agreed with them. So maybe that's also something I could look into, is creating a government index of how much leeway a governor has over his or hers executive orders. Another thing could also be vaccine hesitance. There was actually a data set on CDC where a study was about how hesitant people are with taking vaccines. If you do have
wrap up your quick presentation.
Yeah, I'm almost done.
Okay, great. Yep.
Next thing is the vaccines applied. The data set I had was only on the allocation, not application. Also, vaccine locations would probably help. And then last thing was hospital intensive care capacity. I couldn't find that data anywhere, but I'm pretty sure that's also an important one. And that's all. Thanks.
Yeah, I think that you analyzed the data pretty in a good way. So the last semester, some students analyzed the COVID data maybe 1 year ago. No, the last semester. Mostly they suffer from the time series analysis. So this is why I didn't recommend it to do the time series analysis. And yeah,
that's
it makes
a
sense.
difficult one.
Right. So very irregular data and only less than 1 year of data, about 1 year. So it's really hard. Yeah. Okay. And just I missed one thing. So you originally thought about the dependent variable as the 5 level. So you dichotomize it because you use the logic.
Yeah. Mainly because, well, we had that.
1, 2, 3, and 4, 5, or something like
yeah, 1, 2, 3, 4, 5. Let's see.
that. Sorry.
Where is it? So 1, 2, 3, 4, 5.
Yeah.
Originally, it would have been more, but I decided to just focus on whether it's lifted, eased, or no change, paused, or strengthened. It helps when your data set looks like this. It is 5 different levels or colors. So I decided to do it based on that.
So in a regression model, logistic regression model, what's the response? The response is binary, right?
So they told me if you use multinomial, you can have 5 different responses.
Sure. You used multinomial.
Yeah, I use
logistic.
multinomial for
okay,
that.
I see. Yeah.
As I looked at it, if I tried to use the other one, logistic, as pure logistic, it would have been binomial. That would have been kind of difficult with 5 response classes.
I see. Then 80% is probably pretty good. Yeah. Okay, so do you have any question from the audience?
I have a question about, actually, it's about this no change category, because the no change category strikes me as problematic. Not that, I mean, I think you did a fantastic job dealing with this very problematic data, so I'm not, I'm not criticizing at all. But see, the no change, to me, you could have a no change because the state is at the maximum, or you could have no change because the state is somewhere else, right? So if the state is at the maximum, nothing's going to make it increase the restrictions, even if the cases go through the roof, you know? So to me, in principle, there's some combining in that category that might not be good for the model, because there might be states in that no change category that are really, really different. But that's just really
that was
interesting analysis. And you just had so much that you had to deal with. So
yeah, that was another hard part too. Luckily, the no change ones, they were mainly the ones that, at least at that time frame, they were mainly the ones that didn't really have too many cases. So like South Dakota, Kansas, South Carolina, and Texas. So that was luckily for me at that point. But if it was like in the early stages, that would have been a bit difficult, as California and New York, I think they were one of the earliest states to have a full state lockdown, whereas South Dakota didn't do anything. So both of them would have been in the same category. That would have made it kind of difficult. But luckily, since I did it in 2021, it's based off of that data. Both of those, or all 4 of those states at that point, they had rather low case numbers. But yeah, that was kind of a difficult one to do.
I bet. Thank you.
Yeah, I think that's a good question. Yeah, so basically the dependent variable is loosening or tightening. It's not that, you know, the level of the restriction.
Yeah, that's the big thing. It's based off loosening and tightening. I don't, like I said at the beginning, I wasn't caring about the severity or whether it's effective or not. I just focused on whether they decided to loosen. As one thing I did, the big thing was, one of the most important variables was the amount of new cases, and whether or not that would cause a severe change or not.
Yeah, I think that's interesting. Yep. Okay, so now that we go to the remaining 2, Laura and Colin, who goes next?
I can go.
Okay, so Laura, can you share the screen?
Yeah.
Okay. Yep, you can start at any time.
Can you see it okay?
Yes.
Okay, hello, my name is Laura, and I'm going to talk about the effect of personality traits on career interests in people with visual impairment. The data was collected by Cornelia Chita for a psychology study. 75 Romanian high school students aged 14 to 21 with visual impairment were participated. The parameters analyzed were the Big Five personality test, VSA career interest, Rotter internal external scale test, and the perceived visual impairment level. The objective is to study the effect of personality traits, locus of control, perception of visual impairment on career interests in a population of people dealing with visual impairment. The Big Five personality test is a question-based test where the points you get add up to certain levels of all of these 5 traits: openness, conscientiousness, agreeableness, extraversion, and neuroticism. The higher the score, the higher the respective trait. This table shows what getting a high score in one of the traits means versus what getting a low score means. The VSA career interest is also a question-based test where the points you get add up to certain levels of all of these 6 career interests: realistic, investigative, artistic, social, enterprising, and conventional. You can see in this diagram what all of these are associated with. In my dataset, I have another variable coded as the highest career interest choice out of all of these. The Rotter internal external scale test measures the expectancy or confidence in external control over your life. For example, if the variable is internal, that means that those individuals generally tend to feel like they have the power to control the events in their lives versus external, where they feel like they do not. These are the variables. The first 5 are from the Big Five personality test. They are numerical with a range from 1 to 5. The next 2 represent the same variable, but coded as factor versus numerical, with 1 being the closest to an internal locus of control and external the opposite. The next one, perceived deficiency score, represents how high the participants consider their visual impairment is. And the last group of variables represent the career interests. The numerical ones represent the job inclination of each person for each type of career interest. The job inclination variable is the highest job inclination each person has, and it's categorical, and the whole number is the same as job inclination, but coded as numerical. The formula I used, you can see it below. I use it for both models. The dependent variable is job inclination, which has 5 levels. I use multinomial logistic regression and linear discriminant analysis. The multinomial logistic regression represents an extension of the binomial logistic regression, which only has 2 possible outcomes. For this model, however, the dependent variable is categorical with more than 2 possible outcomes that are an order or nominal, so they are not hierarchical. The linear discriminant analysis is a dimensionality reduction technique used for separating 2 or more classes, and its objective is to sort and categorize classes. To better explain the multinomial logistic regression model and what goes into it, we have these 3 formulas. Pij represents the probability that the dependent variable falls in category J for observation I, and eta ij represents the linear combination of the independent variables. In Formula 1, this is an example of the equation if there is only 1 single independent variable, and I just put it here for simplicity reasons. Formula number 2 is a link function that shows the probability that the dependent variable falls into category J relative to a baseline category, which in this case is coded as 1. And number 3, using the link function, we express the probability that the dependent variable falls into one particular category. Linear discriminant analysis. Starting from the idea of PCA, which is an unsupervised technique, which looks for dimension of the greatest variance, while LDA A supervised technique looks for a dimension that gives maximum separation between means of projected classes and minimum variance within each projected class. LDA assumes all classes have an underlying Gaussian distribution and that every covariance is the same. For the MLM, there was an issue with the perceived deficiency score variable due to the small data set and due to some interaction that the perceived deficiency score had with different variables, which made me change my initial plan if I wanted to avoid significant errors. If we want to interpret this, for example, for the first row, the log of P conventional over P artistic, which is the taken as the baseline, equals minus 0.2284 minus 0.6495 times big 5 agreeableness, and so on until the row is finished. The residual deviance is 176.95 and the AIC is 246.95. By stepwise regression, this model was found as the best one. If we want to compare the residual deviance from before with the residual deviance of this one, we can see that it went from approximately 177 to approximately 195. And the AIC went from 247 approximately to approximately 235. So agreeableness, extraversion, and emotional stability seem to be the most statistically significant, but this might have been just because of the small data set. For LDA, if we want to interpret it, we can see that we have prior probabilities of groups, which represent the proportion of each career interest. For example, 0.16 prefer artistic jobs the most, and 0.13 prefer conventional jobs the most. The group means represents the average result of each predictor for each type of career interest. For example, for people who have an artistic preference, the average score for agreeableness is 3.625. The coefficient of linear discriminants represent the components, and the proportion of traits represents how much the components explain about the data. The formula you see below is the best model out of all of them from LD1 to LD5, and LD1 was chosen as the best one. By performing cross-validation, I got the following. For MLM by 5-fold cross-validation, the accuracy was 31.27%, and the kappa statistic was 0.0422, which actually shows a slight actual prediction and a poor performance. And for LDA, I got an accuracy of 37.33%, which is better than the MLM. In conclusion, the fact that the dataset is small put limitations on making relevant conclusions applicable to the real world. The predictors that had the most statistical influence in MLM on job inclination was agreeableness, extraversion, and emotional stability. The LDA provided the best accuracy, 37.33%, and the best equation of the relationship between the variables on all initially selected variables. According to all statistical parameters calculated and their general interpretation, only minimal proof was found. But considering how small the data, the study is, it actually does not seem that insignificant. In the real world, we can pick a data set and stop working with it if it ends up being difficult to work with, if there are errors, if it's incomplete, or we don't know how to make it work better. We would still have to fix all the errors with it to the best of our ability, according to our own judgment, when we can find even remotely close solutions to similar problems. In cases like these, value is provided because after the analysis, we can make recommendations regarding what is worth looking into or not. In my opinion, a continuation of this analysis with a much larger data set will provide good insights into the relationship between career inclination, personality traits, perceived efficiency, and locus of control. Thank you for listening.
Thank you, Laura. Oh, just one quick question about maybe I missed this. So data, what's the data source?
The data source is a psychology student who collected this study by herself, and I asked for permission to use it.
I see. So is she in Romania or at Wayne State?
Yes.
Or Romania?
Yes.
Okay, I see.
I have a question too. You mentioned kappa as I don't know, this is as a measurement for goodness of fit, or can you explain that more? I haven't heard of kappa for multinomial regression.
So let's see.
Yes.
So after performing the cross validation, there are several statistical variables. One of them is kappa, and there are parameters, so ranges from 0 to 0.9, for example, means that this has a slight prediction, or that was just an example. That's not the actual range. I need to check what the actual range is. But after comparing this number with the ranges that are like the definition of this, my result was that the prediction was slight, and it had a poor performance.
Yeah, so I would say that the error rate is one measurement, but the error rate is higher when the group is imbalanced, right? So the kappa statistics basically adjust that factor. So it's adjusted error rate or something like that.
I think mine's was like 0.3.
That's better.
Yeah, so kappa statistic is worse than the error rate usually because we adjust the, the correct classification by chance, right? So if suppose we have two groups and one group have 99% share, then random prediction, if okay, so suppose that we have binary, the 0-1 variable, and we have 99% 1. Then if we randomly select 99% of the observations as the 1, then basically we have 99% correct, right? We select, all observations as correct, the 1, then 99% correct. So the kappa statistic adjusts that factor. So yeah, so accuracy is 31%. Yeah. Okay, so do you have any other questions? Yeah, so we have the so-called weighted kappa statistic. So that considers the distance between categories. So in this case, I think just the usual kappa statistic is appropriate. But if the 5 categories are ordered, then we should consider the distance between categories. So also that we have the weighted version of the kappa statistic, which considers which categories are closer. Okay, so if you have no other questions, then we will have the last presentation, the Colin.
Hey, can you hear me?
Yep.
Awesome. Just one second. I'm presenting off my desktop, so I'm
Sure.
gonna have to make sure it all works. Can you see my screen all right and hear me and everything?
Yes.
Awesome. Thank you. So I appreciate everyone staying late. Sorry about that, but I'll probably make this quick. I end up running through it always too fast. So my name's Colin Heck, and I was doing analysis and predictions off US Census data. So first, a quick timeline of the presentation here. We'll start with the background of the project, then we'll dive into the data collection that I did, the data cleaning and preview, and then finally we'll look at the models and the results. So first off, the background. My interest in this started when I believe Professor had mentioned a couple times that you could combine data sets with the census data to get better results on things. And I never knew what he was really alluding to. So I did some diving to see what that census data looked like. And I was happy with what I found, which we'll see in a second. But I didn't find a whole data set, so I had to actually create one. And people often talk about how you can like predict of crazy things like, if you're going to go to college or not, and how, like different levels of success based off your zip code alone. And so that was another influence of mine, is I think that's very interesting. Obviously, I think it's pretty sad, but I think it's very interesting. So that's why I predicted both median income and poverty rate off about 40 details about counties. So first, we'll look at the data, and I want to actually just open up. So this is the census's website. Even though they only do the major prediction every decade, they also have these in between census data that it seems like they're more estimates than anything. I'm not sure the specifics on that, but I'm going off the 2019 data for the most part, but it also references the 2010 data as well. There was not more recent data out there, at least that I could find, that was consistent with all counties across the country. But anyways, so this is just a quick overview of what it looks like. There's a lot of rows here, so we're not going to dive into all of it. And I opened up Oakland, Macomb, and Wayne to compare. It's very interesting off the bat of we have, we have all these details. We have how many households, population, what races are people, what education do they have, et cetera, et cetera. It really gives you a great idea of what the county is made of. There's about 3,000 counties in America, just a little over. And since since I could not find a data set of all 3,000, and I'm a computer science background, so this was a very fun project for me. What I instead did is something called web scraping, which is basically making a bot to interface with a website to collect data for you, or that's what I used it in this case. So I got a list of all 3,000 plus counties, and then dug through their JavaScript code, which I know is getting a little nerdy, but in short, I looped through all 3,000 records, or all 3,000, sorry, counties, and then queried the URL and created a CSV for each one, and then combined all 3,000 CSVs into one CSV. And I did all that, automatically. It took a little over 2 hours to run, just because their response rate on the website's pretty slow, and I have to keep it going pretty slow, or else the website thinks I'm a bot, trying to crash the website or something. So anyways, that's just a bit of an idea what went into creating the CSV. Let me get back into present here. It's taking a second. Okay, so now that I had this CSV that is, just to say real quick, the web scraping I did in Python, and then some basic cleanup I did in Excel before then taking it into R, and that takes us up to date here for some of this data cleaning. So I first went through and I deleted some columns that I knew just didn't carry much meaning. And some of them were just so small too. Like it was different details about the companies, like, what types of companies and what type of products are in the area, things like that, where the variables were so small it was hard to use. I dropped some columns that had tons of null values, tons of missing values. You'll definitely see on here, we can go back to this real quick actually. On the bottom here, there's a whole list of different reasons why they don't have data. There's less than 25. There's less than half of a total metric. It's they're not allowed to share this data, et cetera, et cetera. So there's a lot of reasons. So I went through, and so I started with over 60 columns. I want to say it was 65, and got it down to 40 predictors. This was off the manual, so like the manually selecting columns. Then the next thing I did is a lot of the columns, they were like, we can look at this in just a moment here, but there's a set of total firms, but then they also had, 8 different columns that was total firms, but then it's how many, how many firms owned by women, how many firms owned by minorities, et cetera, et cetera. And so I turned those into percentages instead to make them more usable. And then if there was one for male and one for female, I dropped the more popular of the two to just have a baseline basically. So I did a lot of that, a lot of similar things to that too. And then lastly, I put ensuring usable data. That was, I referenced all these K and FN and stuff. Depending on what they were, I had to treat them differently. Generally, it meant just either dropping the column or setting it to 0, because most of those in one way or another meant it basically equaled 0. So let's real quickly look at the Excel. So I wanted to show the columns I use for predicting, but like I said, it's over 40, so it's too many. But this is what I want to reference. So we have here the all firms, and this is the average, but it's the average based off counties, not the average based off population, of course. So it's not weighted accurately. But so here's the general count of all firms, and you can see that these are predicted by the US Census data, and that's why they're not whole numbers. And so I converted these into percentages. What percentage of firms are owned by women, owned by minorities, owned by veterans? So that was some of the work I was doing to get this data much more usable. So now that I have a nice, clean working data set, I wanted to kind of throw the whole kitchen sink at it. I went through our, what models we went through this semester and tried out all the logical ones, basically. The first thing I did, of course, was the multiple linear regression. I also attempted the forward and backward model selection, but that didn't change. There was no results from that using the mass library step.aic. It didn't recommend me changing my predictors. So I'm not sure if there's some more detail or something more I could have done there, but regardless, I kept my data the way it was after those results. So then I have my 5 models here. I compared just the basic linear model, ridge regression, support vector regression, random forest, and then XGBoost. Given the randomness of this of these counties, some of these counties, you have only a few, like, the smallest county in America, according to the census data, has 12 people in it. But then obviously you have big counties too. So I used k=5 cross-validation to get a better idea as how these models would train over different train and test splits, as well as I used cross-validation to tune the hyperparameters. So I'm flying through here a little too quickly, but lastly, we're here at the model results. Like I said at the beginning, I was trying to predict the median income as well as the poverty rate. So that's what these are, and then that's what, and then on the X here we have the models. Obviously, I said I used linear model, ridge, SVR, random forest, and XGBoost. Not really surprising me, random forest and XGBoost outperformed everyone, but it was closer than I expected. It was definitely interesting to see that, obviously, random forest and XGBoost, if you're unfamiliar with XGBoost, in very simple terms, it is like a boosted tree ensemble, similar to what we went over at the end of the tree section. So I'm not too surprised that these were similar, and then these three all had similar results too. So I was very happy with how my models performed. I'm glad that they could be they could be modeled so accurately. When I looked at, we can quickly peek at it just in a notebook right here. When you look at to see the significance, it got very interesting. Ones that I thought were very interesting is like how dense is the population is a big predictor. Do you have internet? What percentage, like what is the breakdown of nationality? What is the breakdown of age? Things like that. Is the population going up or down since 2010? These kinds of things were very important predictors for these models. And it was very interesting to see how it could take details like that you could see this population, it's falling, they don't have internet, most of the people have GEDs, the poverty rate's going to be high. Things like that you could really see there's a strong connection between these details. So in short, I'm very happy with my project. It was a lot of fun. I'm happy to answer any questions.
Okay, thank you. Do you have any questions from audience?
Just one question that comes to my mind is that did you use one specific variable as dependent variable, or you use different dependent variable for using these regression or KNN methods or boosting and random forest?
So are you asking which I predicted off, like which columns I
Yes.
predicted off?
Yes.
Yeah, so that's what I was trying to show with the, let me get back to the Excel real quick. So this is about 40 plus columns wide, and then these last two are the two different, like, Ys, the labels I was trying to predict, or however you want to say that. But for all the models, I used all of them. All of these columns here to predict off for all the models. Like I had mentioned, I tried the stepwise model selection and didn't get any results. So I ended up just keeping all 40 plus in there. And that's how I got my predictions.
I see. Thank you.
Hmm.
Yeah.
Colin, I was just wondering, did you use and I apologize if you already mentioned this, did you utilize the API to pull down the CSV values? Is that how you went about doing that?
So I couldn't find an API. That does not
Oh.
mean it doesn't exist. But what
Okay.
I did find is, so right here, if you click more, there is a download to CSV button right there.
Okay.
And so I spent some time looking through their JavaScript code that creates this. And it's basically just they have a URL /CSV/county name with some other
Okay.
thing. And I looped through all the county names from a separate file and just collected them all into a Python data frame and then, then converted it to a CSV.
Nice workaround. I like that.
Thank you.
Awesome. Thank you.
Yeah, I think it's very interesting, the presentation. And these days, the trend is that, the support vector machine does not perform well. I don't know. I think probably, the nonlinear relationship is somewhat included. I mean, the characteristics is the nonlinear relationship between variables. Still, the support vector machine works. But here we have the many variables, and probably that doesn't matter so much. But yeah, I don't know. And you said the poverty and the income are dependent variables, right? Poverty. Both are
that is what I'm predicting, if that's what you mean.
that is continuous.
Oh, yes. Yep. So the
Okay,
poverty
I
rate,
see.
it's a percentage. And then the
Mhm.
income, it's just an actual number of what, we can go take a quick look at it. Median household income.
Median. Okay, I see.
Yeah, median, sorry. Yeah, these are a bit lower. So I forget exactly if
I see.
if there was some processing that went in before there, but yeah, they were both continuous variables.
Yeah. I see. Okay. Okay, thank you so much.
Great, thank you.
Yep. So